Continuing from the previous example, we have some transformations of graphs here. So the next one, we have a tangent graph, so our base function, f of x, is going to be tangent of x. Notice that you can't just write tangent because it is a function. It needs to have input, so it needs to be tangent of x as the base function. Now we're going to look for transformations, and I see 3 of them. There's an outer reflection, so that's going to be reflected. It's a y reflection, so the y values go down across the x-axis. So we'll say it's reflected across the x-axis. Then we have an inner 1/2, so that is a horizontal or horizontally stretched, or the 1/2 is going to stretch it by a factor of 2. A 2 would be a shrink by a factor of 2. So horizontally stretched by a factor of 2. And the outer 2 is going to be a shift down to 2. Okay, I gotta look back at my previous page just to remember what that next column is supposed to be. It is our y-intercept. I'm just going to label that. That's the y-intercept. And this is the domain range. Okay, so the y-intercept of tangent. We also want to look back at our previous page to recall that the y-intercept of the base graph of tangent is 0, 0. And so we're going to be looking at moving that 0, 0. So first of all, the horizontal stretch doesn't do anything to it. It's going to keep it at 0, so that's good. And then we're going to both shift it down 2 and reflect it across the x-axis. The reflection doesn't do anything actually because 0 times 0, -1 is still 0. But then we're going to pull it down to 2, so it's going to be at -2. Okay, domain range. All right, here we're going to have some domain changes. When the domain was all real numbers, I didn't have to worry about changes. But the domain of tangent is all x that is not pi halves plus n pi or k pi. We called it k before, it doesn't matter what you call it. And so we are going to have to do the horizontal stretch on this. So if our graph is stretched by a factor of 2, then these are going to double. So instead of these asymptotes being at pi halves, they're going to move over to pi. So the first one's going to be at pi. The next one's going to be at 2 pi. So they're going to be pi wide. So they're actually going to be at n pi or k pi. I prefer to use k. If you want to use n like they've been using here, that's fine. So they're going to be at k pi. So it's going to happen twice as often. So I could take the domain that I have right here and multiply it by 2 just to illustrate. So they were originally, I don't have a lot of room down here, so I'm going to do it up above. So they were originally at pi halves plus n pi, and we're going to double those. And so that's going to be pi plus 2n pi. Let's see. So actually, I did not do that part correctly. We're going to modify that. Because I have pi plus 2n pi, that's going to simplify to, it's odd, right? Because that's even plus 1 is odd. So it's going to simplify to 2k plus 1 pi. It's just the odd multiples of pi. So the domain, I forgot to even write the x not equal to, so we just messed that up the first time, but luckily we are able to fix it right here. So this is all x not equal to 2n or 2k plus 1. That's how I would call an odd multiples of pi. So if I double this, it's going to pull pi halves over to pi. It's going to pull pi over to 2 pi. So at 2 pi, we're going to go through the x-axis. So we don't have every multiple of pi, we just have the odd multiples of pi. So this asymptote that was 3 pi halves gets doubled to 3 pi. So I want pi, I want 3 pi, I want 5 pi, etc. Double each of the asymptotes. So I want just the odd multiples of pi halves here. All right. So there we go, that's our domain. So as you can see, the domain is much more complicated, having to deal with the restricted domains in the tangent and the other functions than it was in the sine and cosine. But the range is going to be a lot easier because the range was negative infinity to infinity, so that's going to stay the same no matter what the transformations are. If you multiply infinity by something, it's going to stay infinity. So the range is negative infinity to infinity for tangent. We're going to get a chance to look at another domain practice when we get to the next one. Make sure we can do this correctly. So I'll make it use that same technique we did. We doubled because we had a horizontal stretch by a factor of 2. So we're going to double that original domain. Okay, so let's take a look at the next one. This is a cotangent function. So its base is cotangent of x. And then it looks like just 2 transformations. I have a left shift of pi, and we have an up shift of 1. All right, so how does this affect the y-intercept first? So if I look back at cotangent's original y-intercept, ooh, it doesn't have one. Now, it will maybe, depending on the shift, have one if you shift it left or right. If I shifted this one, say, left by pi halves, it would give me a y-intercept of pi halves. If I shift it left by pi, since pi is also an asymptote, everything that's at pi is going to move over here. So I'm going to still have an asymptote, so there won't be one. So there's no y-intercept here. But if I was shifting by pi halves or by something that wasn't pi, I may get one. In this case, pi, where pi is, shifts left, so I still have an asymptote right there on the y-axis. All right, and then our domain and our range. Okay, we might as well do the range first because the range is the easy one. It's infinite, negative infinite to positive infinite, so our cotan range is going to stay infinite no matter what transformations I apply to it. You take infinity and you add 1 to it, you're still at infinity. Now for the domain, okay, so the domain was originally you can't have all multiples of k pi or n pi, and so if I shift that a full pi unit over, that's going to shift every other asymptote over as well. We are still going to be at k pi. So we'll have x not equal to k pi, or they write n, I just like k, it's just preference, so k pi, n pi. X can't be those still. So this one's not multiplicative, it's additive. And so if I make a note of that over here, if I already had x not equal to k pi and I added pi to it, that's just k plus 1 pi. But since k can already be odd or even, that's just the same thing as a new k pi, because I don't have any knowledge of whether k is even or odd. The reason it was different in the last one was that I had the 2n, and so no matter what n is, 2n is even, and so 2n plus 1 will guarantee to be odd, and that's why that one made a difference and why I had to write that one in the 2k plus 1 pattern. I don't here because k plus 1 will be odd if k is even, and it will be even if k is odd, so it's just some multiple of pi. Okay. Okay, on to our next one. We're looking at a base function here of cosecant of x, and it looks like I see 3 transformations. The 3 here is going to be a vertical stretch by a factor of 3. Then this 2 is going to be a horizontal shrink by a factor of, it's a shrink, I apologize, it's a stretch, it's a stretch, it's a stretch, because as a horizontal, getting myself backwards, back to the first time. Sorry if I'm confusing you guys. I really need to focus on this right here. It's not a stretch. I was right the first time. Goodness. All right. I just did a vertical stretch. This is a vertical stretch because it's larger than 1. That's standard. If my horizontal number is larger than 1, it's the opposite. It is not a stretch. It is a shrink. For some reason, I second guessed myself. Sorry about that, guys. It is a shrink. So it's going to be a shrink by a factor of 2. Not a stretch. It is a shrink. Opposite of the verticals. Verticals larger than 1, stretch. Horizontal larger than 1, shrink. Then it also has a shift to the left, but how much? So the 2 right here needs to be factored out. So if I think about this as 3 times cosecant of 2 times x plus pi over 2, it's really a left shift of pi halves, not pi, because remember that multiplicative needs to be factored out. Okay, so for y-intercept on this one, all right, which am I looking at? Cosecant. So the cosecant function originally did not have a y-intercept.